stoichiometry. That is going to talk about converting, and we're going to use mole ratios. Before performing any calculations, you have to have your equation balanced, and you have to make sure that, you know, everything, the mass and atoms and everything are conserved by balancing the equation. Each stoich problem is different, so you have to kind of go into it and look around and see how it's set up. The coefficients from the balanced equation then are going to help you build the mole ratios, and that's going to give you a stoichiometric ratio to be able to determine how much product you're going to be forming. So in some cases, you are given information about one of the reactants, and they're going to tell you automatically that that one is the limiting reactant. In other cases, though, you have to do the calculation, determine which one's going to be the limiting reactant, and then the other one's going to be excess. Sometimes they'll even ask you how much of the excess remains. In a lab situation, you're going to be predicting how much product might be produced, but sometimes that doesn't actually happen. You don't get as much as you think you should. And so that's going to be your percent yield. And we'll talk about calculating all of those today in some of our sample problems. Tomorrow, you're going to be doing a lab where you've got to figure out which one is the limiting reactant, which one's the excess reactant, how much you should be making, how much you actually made, and so forth and so on. All right. So theoretical yield is the calculated amount. So that's what your BCA tables are going to give you. Actual yield is how much you actually ended up with. Your actual yield typically, or almost every time I've ever seen it, will end up being less than your theoretical. So in theory, you should make more than your actual. And back in chemistry, when I would go through this with you back then, I would oftentimes talk about my chocolate chip cookies when I make chocolate chip cookies. Okay. In theory, my recipe should give me about 64 cookies. And it does when my husband's not home. When he's home, though, he will come in and usually sneak some cookie dough. And then I don't end up with 64 cookies. I end up with less. So my actual is less than my theoretical. Okay. So I talk about like your theoretical kind of being your recipe card, what your recipe card says you should have. And then the actual is how many you actually end up with. Okay. And you can think of your BCA table as kind of your recipe card. All right. So here's our first problem. We have how many grams of water can be produced from decomposing 1 gram of hydrogen peroxide according to this equation. They were nice and gave us a balanced equation. I'm going to rewrite the equation just so that I have more room to work. This is kind of small for me to write, especially with this pen tablet. Okay. So remember with our BCA tables, and you may have, depending on who you learn to do stoichiometry from, you may have learned to do this in a dimensional analysis kind of or factor label method. I use BCA tables, and the reason why I use BCA tables is A, they're easier. B, you get your answer a lot faster. C, they're going to lead into something in Unit 7 that's called an ICE table, which is set up the same way, but stands for initial change equilibrium. So when you get used to these, it makes the ICE tables a lot easier. All right. When you work with these, you can only have moles in here, or if you're doing gases, you can have liters in there. So that's the other option that you can have sometimes with BCA tables. But for what we're working with right now, we're just going to do moles in there. So you've got to change these into moles. Okay. So get your hydrogen peroxide changed into moles. You're going to take that 1 gram and you're going to divide it by the molar mass of hydrogen peroxide, which is 34 grams per mole. And when you do that, you're going to end up with 0.0290. Now, when you use my BCA tables, you need to have at least 3 sig figs in each of these holes to make it work right. If you are lazy and try to do this and only have 1 sig fig in here, like if you had 0.03, you're oftentimes not going to come out with the right answer. So make sure you have at least 3 sig figs in there at all times. Okay? All right. So before I start this reaction, I don't have any of these things present on my product side. In order to figure out how much of this stuff I need to go up into the cloud. Okay, so I'm going to go up this way. When I go up, what process do I use? Division. So I'm going to divide by this by whatever coefficient I have present here. Okay, so I'm going to divide here. So I call this my cloud up here. Okay, that takes me into the cloud. I end up with 0.015 for my cloud. It's probably 0.45. Let me grab my calculator. 0.145? Okay. All right. Now, when I come down out of the cloud, what operation do I perform? Multiplication. Exactly. Now, I don't have anything to multiply here. What is this guy right here? 1. A 1. So that ends up being the same thing here. Now, for this side, I'm going to subtract that amount because I'm using it up to make the stuff over here, so they get added. And then my change amount down here is how much I've got left over. So for here, I take this, I subtract this, and I end up with 0. Here I've made 0.0290 moles, and here I've made 0.0145 moles. They want to know how many grams of water can be produced. So I'm going to take this value and do what with it? Because they wanted to know grams. How do I turn it into? All right, so I'm going to multiply this by 18.0, which is the molar mass of water. And when I do that, I end up with 0.53 grams of H2O. Why only 2 sig figs here when I was making you carry 3 up here? Right, this is your measured amount. You want to end up with the same number of sig figs in your answer. All right, questions on that stoich? All right, so that was an intro problem. We're going to do another one here. This one deals with limiting reactants. So you've got to figure out which reactant is holding you back from making more stuff. So again, like with the previous one, I am going to start out by writing this out just so I have more room to work. Okay. I'm going to set up my BCA table down here. It's hard to do straight lines with this pen tablet. All right, so here's my B, my C, and my A. I've got to take this iron and convert it into grams. Okay, so 15 divided by iron is 55.9. Again, at least 3 sig figs. All right, now they were little stinkers here and gave me 66.5 liters of this, but it's at STP. So at STP, if we have 6.5 liters, okay, we know that for every 22.4 liters, we have 1 mole of O2. So that's where I got this.
Where did you get 22.4 liters? Or is it just like
this is Avogadro's principle that at STP, any gas, no matter what its identity is, you've got 22.4 liters of that is going to equal 1 mole of that gas. Standard temperature and pressure. So standard temperature is 273 Kelvin and pressure would be 1 atm. All right, so now we are going to end up with 2 different clouds forming. Okay, one cloud is going to take this value and divide it by 4. One cloud is going to take this value and divide it by 3. Again, keep at least 3 sig figs in this process.
I'm sorry, Libby. I'm so invested in the swimming career. They're not telling me anything. She thinks freestyle is where you get to choose whatever you want.
Well, technically it is, but you're going to choose the fastest stroke.
But she thinks it's like freestyle kicks like backbeat. No, I don't. I thought like if it's freestyle, you could do like backstroke.
You could.
You can.
What? You can.
Then why'd you say that you had to do freestyle?
Because your front crawl is going to get you there so much faster. It's the fastest.
Why are you guys acting like I was stupid when you could actually do backstroke?
You could. You're just stupid.
Libby, they were being so mean to me yesterday. You guys.
All right. So hopefully, hey, me. It's about me right now. At this point, you've identified your 2 clouds. You are going to pick whatever is the smallest cloud and get rid of any others. So this cloud's going to go away. You're not going to use him anymore. He's done. Do you see how we pick the smallest cloud? Then it doesn't matter. You're going to end up forming the same amount. So it's irrelevant. You're trying to figure out which one's limiting you. So they would both limit you at that point. You'd run out of both of them at the same time. Evie, did you follow me?
Yes.
Okay. So we've got, did you see how I got the 2 clouds?
I see how you got the second one.
So I took this, I divided by 3 to get this one. This divided by 4 to get this. So whatever your coefficient is below that number, you're going to divide by it. Yeah.
How'd you get 0.0675? Because I got, like, the last number I got 1.
So 0.268 divided by 4.
Because I used
Oh.
2683 divided by 4, and I got 0.06.
Okay, so 15 divided by 55.9 is 0.268. And then if I divide that by 4, this would be a 1 here, I guess, right? Is that what you're saying?
Yeah,
This should be a 1? Okay.
if you round it up.
There. Okay, sorry. I'll fix that. All right, good. So take this value. Do you know how I got this value, Evie? Okay, take that, divide by 4. That gets you this value. Good. Then you look at the clouds. Get rid of any cloud that's bigger than the lowest one. So if there's multiple clouds here, get rid of everything but the lowest one. Then you're going to take that value and you're going to multiply it through the coefficient to get this value. So multiply it by 4, multiply it by 3, and here you're going to multiply it by 2. Oh, shoot, I screwed up. Okay. These are going to be plussed on this side, and we're going to be subtracting on this side because we're using these materials to make these materials. All right, so we're going to make 0.134 moles of this. I'm going to, what did I do here? I just brought down the value, didn't I? I didn't multiply it. Ay, 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 there. All right, and then 0.29. So this is how much I'm going to have left over of the oxygen. This is how much iron oxide I will have made, and I won't have any iron left over. So how many grams of rust would it form? We need to take this value and multiply it by the molar mass, which is 159.7. And that ends up being 21, how many sig figs? 2 sig figs, so 21 grams of iron 3 oxide.
But can we use more than 3 figs, or is that not?
Yeah, you can use more, but at least 3 sig figs in the boxes and the clouds. Everywhere in this operation up here, you want to have at least 3 sig figs. But then when you're going for your final answer, go back and look and see what the measured amount was. Well, we had 2 sig figs here and 2 sig figs here, so our answer should be 2 sig figs. But keep consistently at least 3 sig figs in this table and in your clouds. All right. Remember how to do stoic now?
Mm-hmm.
All right. So next problem is an I do problem. Combustion analysis. Oh, that's right. I have combustion analysis that I added into your notes, didn't I? Fun times. Didn't I add this in?
No, I don't see that. Yeah, I don't see it.
Okay, well, we'll skip over to the high do for right now. All right, percent yield in a reaction, we've got 46.1 grams of cesium, 13.4 grams of oxygen, and we're collecting 28.3 grams of cesium oxide. This is my actual amount. So I'm going to need that for my top number, where I go that over theoretical times 100. So I won't need this until the very end. Okay. So I'm going to start off. I'm going to have my cesium. It's reacting with my oxygen. Remember, oxygen's a Brinkelhoff. And it's going to form CS2O. And I need to balance my equation. So you have to start out with a balanced equation. So I'm going to have to put a 2 here and a 4 here to get my equation to balance. I'm going to take this and I'm going to divide it by the molar mass of cesium, which is 132.1. I'm going to take this and divide it by the molar mass of oxygen, which is 32.0. That's going to give me my mole amounts that I can feed into my table here, which are 0.347 and 0.419. So I'll give you a second to catch up on your writing there. Good. Then we're going to take these and we're going to make our clouds. So we're going to make 2 clouds. I'm going to take the 0.347 and divide by 4. That's going to give me a cloud here of 0.0868. And then this guy I divide by 1, so 0.419. So this is my smallest cloud. I'm going to get rid of this one. Then I'm going to take this value and multiply through the coefficients until I get down to this change table section. So multiply this one by 2. I'm going to be forming product here. So it gets a plus, and I'm going to be using product here. So it's going to get a minus. All right, so those are my mole amounts. I then need to take this mole amount and turn it into grams so I can work with the material that I have up here in the problem. So I'm going to multiply this by the molar mass of cesium oxide, which is 281.8. And that ends up giving me 49 grams. So if I made 28.3 grams and I was supposed to make 49 grams, that's going to give me a percent yield of 57.6%. 0.8%. All right. So take a minute to do the we do, and we'll come back and talk about your answers on that.
Yeah.
What's the leader constant?
22 point.
You don't use it in this problem. It's 22.4, but don't use it in this problem. So they gave you the molarity here. Remember that molarity equals moles over liters, okay? So take this, convert it into liters, which is 0.05 liters, okay? That's going to, over X is going to equal your molarity, which in this case is 0.25. So take this times this, that gives you this value, or this value actually. I guess it gives you both. Okay, so here we are starting out with the same number of moles, but our clouds are going to be different. Okay, so this cloud here is going to be 0.00625. And this cloud is going to be 0.00147 or 17. Oh, I'm getting dyslexic, y'all. Sorry. 0.00417. There we go. My apologies. All right. So this cloud is greater than this one. This is my smallest one. So I'm going to use this for all of my calculations. I'm going to bring this down through here into here. I picked the wrong thing here. It's psychedelic in my colors. I'm going to bring this one here. This is a 1, and then this will multiply by a 6 to get it down to here. Okay. So this guy here, we're going to end up using 0.00833. Here is 0.0125. We're using these up, so they're minuses. These are going to be pluses. And here is going to be 0.0250. All right, then they wanted to know how much of this I'm going to make. So I'm going to multiply that by the molar mass of iron 3 chloride, which is 162.4. When I do that, I end up with 0.677 grams of FeCl3. So for tomorrow, you need to make sure you bring your goggles to class. You need to make sure
Liam Fitzgerald, will you please come to the attendance office? Liam Fitzgerald, please come to the attendance office.
you need to start working on your pre-lab calculations so you know what you're doing in your lab tomorrow, and then look over the lab material. The one thing that I absolutely need you to do tonight, if you do nothing else, which I want you to do other stuff, by the way, but the one thing that must be done tonight is you must read through that procedure so you know what you're doing when you come in here tomorrow. Because if you have to spend the time reading through that procedure and figuring it out, you're not going to have time for the lab. Good? Okay.
What if we don't have goggles? I'll never give you goggles.